individually, I will show you how you can model based to a so-called layout part or layout drawing. How I'm going to demonstrate this with example exercise, or let's say example task. So no exercise is this exercise which I present you is not anything that you must return, but you can of course do it by yourself also. In this Moodle page under the right part modeling, I firstly have two documents. Firstly, the first one is about this different way of modeling. It explains how this is supposed to be working. The idea here is that we create a base sketch including every single dimension that is required for the assembly. In the example, I have created a simple layout drawing of a single cylinder piston assembly, including the piston, cylinder, connection rod, and crankshaft. The idea here is that if I describe the dimension of this assembly in a single drawing, I can easily change the dimension of this assembly. The other way would be to model each, draw and model each of these components separately. The problem there is that if I change, for example, the height of this cylinder, this total height of this assembly, 230 millimeters, in order to maintain the piston position at the same level, I also need to increase the length of the connection rod, and that affects also to the other dimensions. So in this idea of derived part modeling, we define all the dimensions of all the parts in one single drawing. How this is accomplished? One way in SolidWorks is to insert, firstly create this basic drawing of your layout as a sketch, and then use that sketch in different parts. This document here tries to explain how to do that one, but I can show it on this exercise or on this example. The second part of this example is to try to study the motion of such an assembly, how it can be studied with the help of SolidWorks motion analysis tool. I'm not sure how familiar are you with the motion analysis. Have you done any studies of the motion of the components in SolidWorks before?
We didn't do anything during our courses, yeah. So I'd say we're not familiar with this.
Okay. So SolidWorks can do motion analysis of solid bodies to determine, for example, the speed, displacement, velocity. Okay, speed and velocity are the same, acceleration, etc. for different components, for mechanical assemblies. Also, it can simulate, it can reveal. Okay, here is, for example, the speed plot of that part against time as the crankshaft makes one turn. What you can also find out here is for example, the forces that are created during the motion. But let's firstly start to see how this derived part modeling could be used. So here, the base part, it is the part that you can use for the model for this example. So I will download it, save it, and then open up my SolidWorks. Okay, there's quite a lot of open. Let's wait for this to end. Oh, let's wait for this to save. Okay, so let's firstly look at the base part I just downloaded. It might be this one. So it looks like this. Notice that it's quite different to the complete assembly. But if we take a closer look at the geometry that is provided by comparing this picture here. Oh, maybe you don't see so well. Like so. So notice that it is enough in such an example here to only draw half of the assembly and only half of the components, because this is symmetric around this center axis, this concept. Why this? Why the connection? Okay, there's quite a lot of noise or echo. I will mute it. So this is symmetric around the center axis, which means that obviously the location of the other piston in this position is not symmetric, because these parts are the same type. But anyway, I hope you got the idea why only half of it is drawn, because only one half is enough to describe the full layout, so no need to do it any more complicated than it's necessary.
So from the sketch we can derive as many parts as we can?
You can, yeah. The idea of the sketch is to describe everything, or at least the dimensions that are important for the assembly to work as easily as possible. If I take a look at the sketch I've created, notice that everything here must be fully defined. In other words, also what it allows me to do is to, if I change, for example, the angle here 60 degrees, everything else follows. The first thing if you try to do derived part modeling is to make sure that your base sketch will work. I can't change these dimensions, and the geometry stays as it should be.
Why are your dimensions purple? Is it?
You mean the numbers here?
Yeah, because usually they are like black.
Yeah, it's about the SolidWorks settings. This part has been done with different document template, and in the document template, the color of the numbers was set as blue.
So it's nothing to do with properties of the dimension.
No, it's just
like fully defined.
It's just a setup issue.
Okay, clear. Thank you.
Notice that it is fully defined, my sketch, and all the sketch elements themselves are of course black. If something is left undefined, as not fully defined, then this will not work, because there's some elements that are undefined and they will just not work.
Can I ask, like, why is the number in the square bracket indicates?
This is in inch. It means that it is 4 inch. In millimeters, it's 101. Okay, where these dimensions come is from a motorcycle engine that is dimensioned in inches. So it was easier to figure out the rest of the dimensions for the stroke and for the bore, I used it.
Yes, thank you.
More common numbers for that type of a machine. Anyway, the first thing is to create the sketch. And I would say that making this sketch is the hardest part in this kind of a modeling. Because you have to think everything, how to make this sketch work. After the sketch is finished, you do not create any parts to this single part. Instead, this part, including only the sketch, is inserted into a new part. So let's begin a new part. And here, under Insert Tools, I have an option to insert a part into the part. If a part is inserted into a part, it will be there as a document. I can select here, what do I want to bring from my part? If it would have solid bodies, I could bring the solid bodies. If it would have surface bodies, I could bring the surface bodies, axis planes, etc. On this example, I only want to import, I guess, unabsorbed sketches, meaning sketches that have not been used. Okay, it's asking me about document units. I don't want to convert anything. So there is now the sketch from the base part in a new part. Next step is to create one part of this assembly from the base sketch. Let's say we begin by creating this cylinder, this shape here. What would be the most common convenient way to model such a part? With what kind of a feature? It is a cylinder.
It's revolved.
Yeah, revolved post-base. Not extruded. Extruded is like extrude, but revolved. So let's begin a new sketch into the same plane where our sketch is. It's front plane. Take a sketch there. And now, notice, with the sketch tool called Convert Entities, I can convert sketch entities into a new sketch. Also, I can convert feature elements like edges and faces into sketches. By this convert entities, if I select the sketch elements I like to use, I want to use all the lines that make up the cylinder. I select them. I end up with a sketch, fully defined sketch on the location of this original sketch. And of course, in order to create a revolved feature, I need a center line. Center line of the revolve is that one. So convert that one and make it construction line. So it actually works.
So did you just replicate those sketches on top of the
Correct.
existing sketches, or you just changed their properties?
I replicated exactly the same geometry here.
Oh, so we have like two sketches, one on top of the other.
Yes.
So this, great, thank you.
Why should you use this convert entities feature? Is because then it will make absolutely sure that if the base sketch dimensions are changed, also these converted entities will be changing. If I draw a line here, it might change or it might not. Better to use the convert entities, makes it easier to use. Makes it more reliable, let's put it like that. After I have finished my sketch, then it's a matter of just simply using the correct features to create the desired part. in this example, it's going to be that sketch, and that's the first part done. I will call this part cylinder and save it. Now, you should not make any other parts anymore to this very part, because we are trying to build an assembly, a working assembly. So if I, for example, if I would model the piston, this part here, into the cylinder, it would make the two parts fixed. They could not move. Bodies inside a part cannot move, but bodies in assembly can move and operate the desired way. So let's do the same routine. Start a new part. And then let's bring the base part once again. It might be that one. Okay. And let's model the next part.
So what you're doing, sorry for interrupting you, but what you're doing is just inserting a part, a sketch in our case, to the existing part. And then if we change the original sketch, all the other parts will be changed too, right?
Correct, that's the point here.
Yeah. Very clever.
It makes it easier to, because, for example, if we look at the layout here, or let's look at the original sketch here. I have defined the height from the center of this rotational axis to the top of the cylinder here is 275 millimeters. If I now change this dimension, let's say it must be 300. What happens to this part here is called connection rod. What happens to the height, to the length of it?
It increased.
Yes, it must increase, because if it would not increase, then the piston would end up in the original location. Like I said, you could model this type of a device quite well by modeling all the components individually without using this derived technique. But the difficulty comes from if you need to do some kind of a modification or something like that. The drawback of this type of modeling is that the layout cannot be very complicated. It must be relatively simple. If it's too complicated, it's difficult to make the base part in a way that it is actually usable. It might get too complicated quite easily. So for simple layouts and for concepts, this is a good way. But anyway, let's now, for example, model the piston with the same logic, new part, convert entities, and here, the other line must be selected. Did you know that if I right-click a line, there's the option select other, and here I can select which of the lines I select if there are multiple lines at the same location. Instead of selecting the long line, I want the short one. I will also take the center axis directly and convert the center axis to center line, make a revolved. Yes, I want to close my sketch. There's my piston. Delete the bounding box. What is required also for the piston is the hole. So a new sketch. Let's convert that one. And yeah, hole must be drilled through all. Then I would like to maybe make this into a shell. So it's not a solid part rather than a shell-like part. So let's use the shell feature. And let's give it like thickness of maybe 3 millimeters. It's a bit thin, but I think it will work. And final thing is to make room for the connection rod here. So let's make another cut there, which might have, for example, the shape of from the right from there. Edge. Okay, it might cut it quite nicely. So let's mirror this feature, these two lines. Where's my mirror? And it is to mirror that one, that one. It's best practice, try to avoid as much possible to draw anything or add any dimensions in this type of modeling. Because, for example, if I add here a line, it's not defined by any base sketch. But since the length of the line is derived from this line, this edge of the connection rod, it might work okay. But for example, the feature dimensions should be somehow also integrated into the base sketch, but it is a bit difficult, or makes it too complicated easily. But anyway, now let's save it. And next one, let's build this connection rod. Once again with the same logic. Insert the part. Convert the entities. And let's trim that part off there. Now let's give a thickness to this part. For example, 20 millimeters. That's it. In reality, you would also need this lower part of the connection rod, but now it's left out from this simplification of this layout. And finally, we need to create a model for the crankshaft. So the final part, and let's start to build the crankshaft from this pin, from the pin that connects the crankshaft and the connection rod. So begin it on front plane, convert entities, And now the length of this pin must be twice the thickness of our connection rod. So I put length of 20 millimeter for the connection rod. The pin in the crankshaft must be 40. Because the way they are connected, they are on the same pin, so the length of the pin must be twice the thickness of the connection rod. Then these counterweights or webs, they will be located on the end faces of this pin. So we need to begin our new sketch on this face. But we can still, of course, use all the features, all the sketch elements from the original. Like so. Then let's give it a thickness. Maybe 10 millimeters is fine. And finally, the crank journal, the main bearing of the crankshaft, will be located on this face, on the outer face. And let's give that one also a length of, let's say, 40 millimeters. And now it's just a matter of mirroring these two features also to the other side of this part. So mirror around maybe front plane. And there's the model. Without drawing any lines, all dimensions are coming from the base part. After I have finished making all the parts, I can start to build the assembly. Did I show you this trick? That what happens if I have here in under assembly, I am in the insert components feature, and if I select here a part, let's say I select that part, and I press my mouse somewhere here on the drawing area, what happens?
The part will appear where you clicked?
Correct, it will appear somewhere where I clicked. But what happens if I press this OK symbol here?
Oh, yeah, Sima told us about this, I guess. The part will appear on its basic position, I don't know, like relative to the original drawing. And I think what you're leading to is that if we click all the parts and then press OK, they will automatically arrange in assembly because they are derived from one sketch. Am I correct?
Correct. What this does is, if I click here at the OK, it will position the part, this base part, in a way that the part origin is exactly in the same location as the assembly origin, aligned on the same axis. What that means is that, for example, the right plane of my part is exactly in the same location as the assembly right plane. This is quite convenient way to make sure that your assembly will position the parts in a correct manner. And rightly, as you pointed out, if I now insert all my components with the same way, for some reason this doesn't work. It always closes the dialog, even though I wouldn't want to close. like so. I will hide the sketches so it doesn't look so bad. But notice that if I click here the OK symbol, it will make all the parts fixed. Nothing moves. But the position of the parts looks okay. They are now exactly where they should be. Like so. If I want to make a motion analysis of this type of a system, I need to make sure that my model is actually working. So for that reason, we need to build our assembly again. So let's start by making the crankshaft rotate, only rotate around the z-axis. Now it doesn't rotate because it's fixed. If I make it float, then it can move around and also rotate quite freely. So one way to make the part rotate is to think that, okay, I have an origin in the part, and I have 3 planes in my assembly. Can someone say, if I make the planes visible, how could I make the crankshaft rotate around z-axis, but maintain the position of the crankshaft defined? What should I make? Yeah, please say.
Well, I've been thinking about fixing the central axis of the crankshaft, if it is possible.
Okay,
so
I happen to have a center axis called keskiviiva. Where should it be fixed?
Where
I think we should create a new center line that cross between the plane and fit.
Yeah, one way. Yeah, I could create a center line, for example, between the top and right plane, and then make the center axis coincident with that one. That would be one way, which we can do. So let's create axis on the crossing of those one, and then let's put the center line of this part coincident with the, and then it can move along the center axis. That's easily avoided if I made, for example, front plane and front plane. Now it can only rotate. Notice that I could have done exactly the same without this axis. If I made, for example, my origin, the origin of this crankshaft must always lay in the right plane. Similarly, it must be always on the top plane. Because the origin will always be, even though the rotational axis of the part is whatever, it will be always on those 2 planes. Next thing would be to define the location of this cylinder. Why I cannot use the origin to define that one? Is that
because
say, please.
Well, it goes ups and down and a little bit twists its angle because of the crankshaft. Is it?
Yeah, the cylinder is fixed; it doesn't move anywhere. But the problem is that in this type of a motor layout, these cylinders and the pistons must have an offset because they cannot be located at the same journal location. They must be offset by the distance of the thickness of the connection rod. So that's why I need to move my cylinder a little bit. The other cylinder must be a little bit backwards, the other one must be a little bit forwards. So, in other words, the top plane of my cylinder must be with the top plane of the assembly. Right plane must be on the right plane. But this dimension here can be something else. And what defines this one is the location of the connection rod. I will put the connection rod where it should be. So the connection rod must be located from that journal on this pin, like so. This will position so that it's always on that journal. Let's make, for example, this phase surface coincident with that one. Now it's always staying on that one. And finally, I must put to the other end of my connection rod this cylinder piston. Firstly, it must be located here. The pin must be like there. And this face should be coincident with that face. Now, if I put cylinder piston into the cylinder,
But is it correct that you align the piston to the crankshaft side?
Of course, in reality, you would create quite a lot of friction here. Yeah. Please continue what you were saying.
Yeah, I was thinking about like making it with advanced mates and
yeah, I could.
with or anything.
But since this is a layout for two-cylinder, I need the second one besides it, next to it. So like there should be the second connection rod on the same journal. And they cannot be like this, so they must be like that. But in reality, this is not a good way to do a motor or engine. If I have so big surfaces that are touching each other, it will create a lot of friction. So those should be always avoided. But anyway, this is the point why they must be offset a little bit.
Yeah, I totally forgot about the second piston. Sorry. Yeah.
But anyway, then just build the model with the same logic. As you see, this is greatly simplified example of a motor, but it shows the basic principle, how the layout should look like. Okay, now everything should be defined. What does this symbol mean here, this parentheses and the line? What does that indicate?
Which means that it's not fixed.
It's not fully defined.
Yeah, exactly.
Yeah, not fixed, but fully defined. For example, I have fully defined the location of this cylinders, since they don't have the parentheses in the line in the parentheses. The same is in sketches or features. If you see that kind of symbol, it means that it's not fully defined. What degree of freedom is not defined in my assembly? what I have left undefined so far.
The crankshaft can be rotated, yes.
Yeah, so it has that is the degree of freedom I have. The crankshaft is able to rotate, which in turn means that the piston locations can also move. So that's basically how you can build an...
Can I ask a question? Bit not related to that, but is it how located cylinders in W16, you know, that
Yes.
it's located like that?
What is located?
I mean piston.
I think in W16 motors, for example, in Bugatti and Volkswagen also made them, they had two lines of cylinders. I mean, it was like in some motor configurations, I remember seeing that they had two lines of cylinders in form of a V. So there would be another cylinder here and another one here.
Okay.
That's one configuration of a very special type of configuration of a motor, but I don't remember how did they arrange the crankshafts there. Connection rod.
Do you think it's a good idea from engineering point of view? I mean, again, friction and all that properties.
Well, it's quite complicated type of a motor and quite expensive, so maybe it has some benefits. The main benefit is that compared to traditional V motors, like shown here, this is so-called V-twin, because the cylinders are in a V shape and there are two of them. We call it V-twin. It's much shorter if we arrange the cylinders in a row in this type of, it's half of the length. But as for the construction or the concept of the motor, I would say that it's much more complicated because this type of engine layout is very, very simple. Okay, back to the example. Now, if everything is fine, if I now go back to my base part, remember the origin, we started from this one. If I make a dimension change here, let's say I put the cylinder, or this angle between the cylinders to 60 degrees. What should happen in the model?
Should anything happen? Because did we use the second line during the assembly?
Yeah, this is representing the second cylinder position here.
Then consequently they should, the angle between cylinders should be 60.
Like so. Exactly. The same applies if I make a change to the dimension of the basic. Let's say I increase the height of the deck height, so the height of cylinder head. Then go back to the assembly. Once again, it has increased. Okay, let's go back to the original one. So this was 45. This is 275. Okay, finally, the second part of this example is to perform simple motion studies for such an assembly. So imagine that we can rotate our, okay, in reality a motor works like that we have a combustion here that forces the piston up, forces the piston down, and that creates the rotational motion. That kind of a simulation in SolidWorks is unfortunately not possible. It's a bit too advanced. But we can simulate what happens, let's say, for the piston at certain speeds. Let's say that our rotational speed is 100 revolutions per minute. which I cannot rotate this at the speed of 100 revolutions per minute. Instead, we need to use this SolidWorks motion analysis for that. Let's see that I have it active. So now it should open up. And the motion analysis is accessed here in the motion study. Here I can do basic animation. If I select animation, I can, for example, add a motor or rotating element to the crankshaft, and it will create me an animation how the parts move if this part is rotated. The animation is purely a visualization tool that can create different types of animations. Next up is basic motion. Well, it's a little bit more advanced animation, let's put it that way. Here I can add, like it says, I can add a spring gravity motor. Apparently in basic animation I cannot really add a motor. Okay, I can add a motor. But anyway, the basic motion is purely more advanced simulation. Final step is this motion analysis. The most realistic simulation. Okay, maybe it is so, but moreover, it can also describe the results in a numerical format. Because basically, if I know the rotational speed of this, if this is spinning at a constant velocity, I can calculate what is the speed of the piston analytically, because it's basically just geometry. Because I know every time where is the position of this piston. They are all coming from the geometry. How this is solved is purely based to the geometry of the model. It doesn't really take into account any forces in that sense. Or it's just mechanics that it's solving there. One other thing this motion analysis does is that it only will tell external forces. It doesn't take into account what happens in how the force is distributed in a single component. It doesn't tell you what is the stress at a given location. Those can be analyzed with other tools, which are available in SolidWorks, but not in the motion analysis. This motion analysis is only meant to analyze the motion of different components. How I can perform a simple motion analysis is that firstly I need to make some part move. I will put a motor to the crankshaft so it will start to rotate. There's the symbol for motor. Okay, it had already selected the face, but this surface must rotate 100 RPMs. I could also define different types of movement, but let's start with constant speed. And now it created me a motor here from 0 to 5 seconds and spinning at 100 RPMs. Next step is to calculate the animation. And there it goes. Now if I play it, it shows how the parts are moving. If this part is rotating at 100 RPMs. If I want to decrease the length of my simulation, I can do it by moving this key point here. I think 1 second is enough. maybe even a bit short. Let's try to make it 1 revolution. So about there. Under simulation options, motion study properties, I can increase the frames per second. Let's say I put 200 frames per second. Let's see the result then. It's much smoother. So it calculates 200 steps per second. How many frames per second are calculated? If I put like, let's put like 4, I think it will only make a couple of points there. They went very fast. So that is in how many steps we calculate motion study frames per second. Let's put like 200, it goes nicely. After this calculation has completed, I can view the results from the results and plots. And once again, I need to define what do I want to see. If I want to see displacement, velocity, or acceleration, I select that one. Then what type of information I want to see? I want to see linear displacement, linear velocity. I'm interested in the speed of my cylinder. I select that phase and then the component. Okay, let's take the magnitude. And there's what is the speed of this phase at different time periods. If I play my animation at the same time, it goes very fast. If I decrease the speed, let's see if it's then readable. You kind of see where it is going at what locations. For some reason, it's a bit flickering. What can be studied from this graph? What does it mean?
Well, we check the peak speeds.
Yes.
Maybe it can be crucial, I don't know, for rotation or any analysis.
Yeah, but
basically.
But what? How would you describe when is the speed when the speed has the lowest value and when the highest? Of course, I see the time period, but where is this located? By only looking at the graph and the layout. What would you say when the speed must be 0 and when it has the highest value, and why?
Well, it can be explained because a cylinder, a piston reaches its top and lowest position. The head of the piston, I don't know, stays still, while the piston itself makes some rotation to change the direction, and then it starts to go up or down again, and increases its speed and then stops again. So,
and the reason why the speed must be 0 is because, firstly, imagine that, okay, the piston is coming. If I, for example, hide that part, no, maybe I'll do this. Is that if it's coming down, it's going downwards. And at the point where the movement will change to upwards, for some reason my mate broke there, it's going up. I don't know why the center of the axis is not quite correct. Let's see. Okay, now it works. No, it doesn't. There's something wrong in the, see. No, well, anyway, what I was trying to say that if you want to first go down and then go back up, you cannot instantly change the speed from going down to going up without going past the 0 point. So the speed must be 0 every time you change the direction of the movement. It's not possible to change speed without going back. Firstly, stopping the motion. I want to see, does the animation work correctly? Yeah, it does. But for some reason, if I manually move the parts, you notice that the mates broke. Anyway, that was about the example in how to create assembly based to a base part and a brief introduction to motion analysis. Like I said, this was only an example, no need to return anything, but of course if you want to do it by yourself, you're totally advisable to try this one by yourself. For this time, I hadn't thought anything else, so in case anyone has anything to ask, please feel free to present your question. We can do it either here or we can take a breakout room or you name it.
Yeah, I have some questions, but about other exercises. So
yeah,
we can do in another room or something.
Yeah, I can do.
And
How about, yes.
also, I have some question. I do it like you, but like somehow there's no motion analyze in my.
Make sure that you select the add-in motion analysis to be active. I didn't know here add-ins, and make sure that you have SolidWorks Motion available as an active add-in.
I forgot to add it.
Then you can make the SolidWorks Motion is not part of the standard SolidWorks versions. It's only included in the premium and professional versions.
Yes, it.
I don't remember. Was it available actually in the educational version? Might be that it's not. It has to be.
Yes, it appears in my person.
Yeah, it is. Of course it is.
And can you show me again, because I cannot adjust it. So can you show me again how to?
Go to add-ins here. Oh, wrong button. Here. Here, add-ins. Click that one and there. SolidWorks Motion.
Yes.
Make sure that you have it active.
Yes.
Active add-in. Then go to Motion Study. Then here select Motion Analysis.
Yes. And I have to set the rotatory motor.
Yes, to the part you want to rotate.
And what else do I have to do?
The results will be shown here. Results and plots. But for now, I need to move on with the questions presented. So I make the breakout room.
Eero, can I ask you first? I missed the first 5 minutes of lesson, and do we have to return that exercise or no? Because here is no here is no place to return it. And
Like
this has
said,
question.
this was only an example that you can complete if you want, but no need to return it anyway.